Greetings from Team Shunya, from IIT Team Kanchipuram in collaboration with MCC Chennai. I am Manas Narayan, currently the lead of Team Shunya. We are presenting you the second generation of rover Bacha. We are a students club named Mars Rover Students. This club comprises of BTech students who are doing their majors in computer science, electronics and mechanical engineering. We are currently focusing on building autonomous UGVs and robotic arms. Our problem statement revolves around the exploration of inhabitable zones. Our goal is to build a system that can withstand any possible terrain. Currently, to reach our goals, we Team Shunya are participating in different road challenges all around the world. The team comprises of 5 teams: software team, electronics, mechanical, science and marketing team. These 5 teams ensure to manage the different aspects of our club, from our technical systems to our outreach events.
Master team who manifest and develop UGVs and robotic prototypes for industry-ready autonomous systems. We focus on integrating various subsystems that are industry-ready for robot systems. As we know, innovation happens when there is a thirst for improvement, and ERC provides such a perfect platform for teams all over the world to participate in. Our designs satisfy all the primary requirements that are integral for the ERC 2023 competition. In this way, we propel innovation in all systems or system design.
The primary task of the science team is to select the landing location for our mission. And for this, the science team utilized the powerful tool JMAS. JMAS grants us quick access to a vast collection of maps, millions of images, and vector data sets gathered from planetary missions. During the competition, our specialized science gets deeper. We collect rock and soil samples. These samples are essential for the science team to formulate hypotheses from specific region on Mars, which will be mentioned in our science report during the final competition. To determine the most suitable path for the rover, our science team conduct a true analysis of the terrain. We prioritize path with slope below 45 degrees and avoid area with an abundance of rocks and craters.
जब मैं बोलूँगा तो अब स्टार्ट करो.
The rover's mobility rests on a 6-wheel rotor-propelled suspension system supported by a differential bar. This allows a consistent ground contact while fostering safely.
The suspension design optimizes wheel mounting as a fully supported beam configuration instead of cantilever beam. This design aims to reduce drive motor loads, enhancing motor and operational safety. The inner wheel hubs are designed using generative design and manufactured using PETG, contributing to stiffness and strength, while flexible TPU tires on the outside.
हो जाएगा, टेंशन मत ले यार, चल तू.
Greetings, this is cycle for the mechanical lead of Team Shunya. For precise maintenance and adaptive manipulation, we have devised a 6-gear manipulator. The link lengths and the gear of the manipulator have been calculated after taking into account the storage area.
The first link employs a linear actuator for precise arm movement, while later links use high-torque RMCS Rhino encoder motors with timing pulleys that distribute weight for reduced torque needs. The linear actuator's precise positioning is calculated for optimal operation and maximum workspace. A camera scans ARCO markers aiding scene reconstruction. Control interface with a base station GUI for operator input.
Hey there, we are the electronics team of Team Shunya. We focus on building the control system for navigation, maintenance and science cars, power distribution system and a communication system.
Custom-made PCBs have been designed and manufactured by us to ensure equitable power distribution and efficient wire management. In addition, for each individual subtask like navigation, maintenance and science cache, task-specific PCBs have been designed. PID mechanism has been integrated with all 6 mobility motors to ensure seamless movement over rugged terrain during the navigation task. The rover's power system utilizes a combination of 24-volt source and 2 12-volt sources in parallel. This configuration ensures that even if one of the 12-volt batteries fail, the rover's functionality remains unaffected. Furthermore, in the event of a 24-volt power failure, the 2 12-volt batteries will automatically switch to a series configuration, guaranteeing continuous power supply to the mobility systems.
Limiting switches are essential safety devices present at each link of the manipulator to restrict the motor's movement within its minimum and maximum positions. They ensure safe operation and aid in homing the manipulator accurately.
In case the rover starts to malfunction, an easily available onboard kill switch is present, which ensures a power cutoff for the entire rover. In case the main communication system fails, the backup communication, which is LoRa here, will come in place and give necessary telemetry operations such that the rover can reach to the base station safely.
Our software team majorly works on developing two different software stacks, the autonomous navigation software stack and the autonomous
In the planning
manipulation.
stages, with an autonomous manipulation
Now we will look
that
into the
seamlessly
details.
integrates real-time object detection and decision making. This innovative system acquires continuous video from a camera, utilizing advanced segmentation and YOLO object detection algorithms. It then aligns pixel coordinates and the camera's coordinate system, enabling precise object positioning. The decision-making process shapes destination poses or positions that the motion planner employs by considering the environmental obstacle model and intended destination. The real-time object detection algorithm defines probing trajectories in autonomous mode, complemented by established paths for added resilience in the face of potential idleness. In terms of safety, the system employs detected obstacles and the AR tags to introduce collision objects into the virtual environment, effectively preventing collisions during motion planning. This proactive measure guarantees operational stability. The system's expertise extends to the strategic arrangement of objectives and manipulator positioning. These decisions are made with a forward-looking perspective, accommodating forthcoming actions by the manipulator. Precision and responsiveness also characterize specific actions like pressing buttons and manipulating probes. These actions are calibrated in real time using live video feed and IMU data. In the event of action failure, recovery mechanisms kick in, underlining the system's adaptability. To ensure progress and quality, the completion of every task is systematically verified.
The system capitalizes multiple state estimation nodes, each contributing odometric data from different frames. This orchestrated approach minimizes frame shifting and error accumulation. Leveraging this precise localization, we execute behaviors tailored for the diverse tasks. Using NAV, a potent global and local planner, we traverse dynamically generated obstacle cost maps. For the seamless execution of our navigation plans, we rely on the move-based action and simple action client libraries. Further, to fine-tune the precision of our localization, we meticulously calibrate the covariance matrices of our state estimation nodes. These adjustments are done considering the unique inputs from our IMU data from Z to I. Our system also re-evaluates its localization when detecting and scanning AR tags. This recalibration process ensures our autonomy remains unwavering and accurate. Our system is not solely about planned behaviors, it's about real-time decision-making and responsive recovery mechanisms. This dynamic approach safeguards control and stability throughout our autonomous operations.